All right, so I'm on slide 24 of the Chapter 11 PowerPoint. Again, the PowerPoint is in D2L or shared class files. Slide 24. I promised in the last slide I was going to get into an example. I got ahead of myself. There's one or two more slides. So we introduced all the intermolecular forces. We got London forces, dipole-dipole forces, hydrogen bonding, and ionic. There is one more that will come up specifically in Chapter 13. When we form solutions, and I dissolve, like let's just say I dissolve sodium chloride in water, I'm going to have a kind of what I call a mixed interaction, where the sodium chloride, when it dissolves, breaks into ions, but then the water molecule has dipoles, and I'm going to get an interaction between the ions of the sodium chloride and the dipole of the water. So the name of that force is an ion dipole force. Okay, it doesn't really come up with pure substances, because you have to have two different things involved, okay? So this is a force that involves solutions. It is a strong force of attraction. It will be important in Chapter 13, but it's not going to be important for this section, okay? But this chart in the PowerPoint kind of helps you go through the process. If you're looking at a molecule and you want to decide what kind of force it has and all that, this organizes some of that information. All right, again, that's what the ion dipole forces are, so I'm going to move on past that. So here we go. I have a set of molecules. The rule is I want you to figure out which ones are going to have the highest boiling point, which ones are going to have the lowest boiling point, put them in order. Key here is if you have to do this on a worksheet or on the test, make sure that everything is labeled clearly. Make sure you tell me which way your low boiling point is starting on and then the high boiling point. Just label it clearly so that we can tell, or we're going to count off points. If you just make a list but don't tell us which side's the higher or the lower boiling point, then we can't grade it accurately, okay? So, if you're going to do this, first of all, you need to draw the molecules out, okay? So, stop the video if you need to, draw out all these molecules so you can see what their structures look like, and then we need to classify them and determine, okay, which ones are going to be ionic or hydrogen bonding or London forces or dipole-dipole forces. We need to figure those out. Based on that, if you go back a couple of slides, we're going to rank them based on the intermolecular force first. The ones that have the same intermolecular force, we're going to compare their molecular weights. And then the ones that still have the same molecular weight, then we're going to come look at how much branching they have off the straight chain. Okay? So, go ahead and figure that out and then restart the video when you're ready to. All right, so I drew out on this board. So essentially what I have, I've got my CH3, OCH3. It's called dimethyl ether right here. And then ethanol is the second one. Butane is the third one. You don't need to know the names, so don't worry about the names. Those are organic names. Then I got my the C4H10. There were two structures that referred to. So one of them is going to be a straight chain, and the other one's going to be a chain of 3 carbons where one of them branches off. Then I've got my NaCl, my MgO, and my CSI, and then finally CH4. Okay, so what I would do right now, I know that the lowest boiling points are going to be the ones that are nonpolar molecules. So if I look, CH4 is going to be nonpolar, and I know that means it's going to have London forces is going to be the strongest force that it has. Same thing for that one, and that one. Those are all nonpolar. So I want to rank them and say, okay, I'm going to start, let's see, there are 1, 2, 3, 4, there are 8 molecules. So I'm going to say number 8 is the lowest boiling point. So of the nonpolar molecules, the smallest one is going to have the lowest boiling point. So CH4 is going to be number 8. It's a nonpolar molecule, it has London forces, and it's the smallest one by molecular weight. Okay? Now, a key to this, if this is on the test, I often make this be a written question where you have to explain your work. You have to be able to tell me how you know it's number 8. Listing them, if it's a 6-point question, putting them in the right order from 1 to 8 might get you 2 points. But the explanation for how you ranked them is going to get you the other 4 points. Okay? So the explanation is important. Make sure that you can put what I'm saying in words, make sure you can put it down on paper. Okay? Now, of these two, They're both nonpolar, so they both have London forces. The one that is a straight chain is going to have stronger interactions than the one that's branched. So therefore, I would say this one is going to be a lower boiling point than this one. So this is number 7, and this one's number 6. All right? So then we look up and say, okay, well, what about this one? Now, some people, the way I drew it, some people might look at that and say, oh, it was nonpolar too. Okay, well, that's a bit of a trick. You have to watch out for it. It looks like the oxygen has a carbon on that side, a carbon on that side, and if they're on opposite sides, you might think that the two carbons cancel each other out. Like each bond is polar, but if they're arranged symmetrically, they cancel out. But we're overlooking something. I drew it that way on purpose because a lot of times in the book you'll see it drawn that way. But you have to remember oxygen, if it has 2 lone pairs and 2 bonds, the oxygen atom, the electron geometry is actually tetrahedral. And when you have 2 bonds and 2 lone pairs, the molecular shape is actually bent. So the 2 bonds around that oxygen should be bent at an angle of about 109.5 or a little bit less. But that means it's going to be polar because the carbons coming off the oxygen are not symmetrical. They're both coming off this way. So on the back side, the oxygens can have a partial negative on it. Okay? Again, that's something you need to practice or look back at in chapter 9 if you need to. Okay? But, so this is going to be a polar molecule. But then the difference between these two, which again, they have the same chemical formula. This one, though, the oxygen is not connected to a hydrogen. In this one, the oxygen is connected to a hydrogen. So this one has hydrogen bonding. This one's just a regular polar molecule. So dipole-dipole forces versus hydrogen bonding. Dipole-dipole is going to have a lower melting point because it's a weaker force. So that's going to be my number 5. The one with hydrogen bonding is going to be my number 4. And then that brings me finally to my 3 ionic compounds, which ionic compounds are going to be way at the top of the list. When I look at these, though, this is something we haven't talked about yet. I have to go by the formula that we showed in the beginning. The force of attraction is based on the charges on the top and then the radius in the bottom of that equation that we showed. Okay? Now, why that's important. When I compare these, the first thing I might do is look at the charge. Sodium chloride is +1 and -1. There's a certain attraction between charges of +1 and -1, but then magnesium oxide is +2 and -2. That's more charge. If the charges are greater, then the attraction between them will be stronger. So MgO, because of the increased charge, is probably going to have a stronger force of attraction, which means it'll have a higher melting point and boiling point than NaCl. Now, another factor, though, is also size. If I look at the sizes, Mg and O, they both are going to be isoelectronic with neon. So basically, they have their second electron shell is full. With sodium and chloride, sodium is second shell, but chloride goes to third shell, so it's bigger. And if you remember in that equation, the radius was in the bottom. If you increase the radius of the atoms, the force will actually decrease. So sodium chloride has less charge and it has a bigger atom involved. So both of those are going to make it have a weaker attraction. So basically MgO is going to be the strongest attraction because they're small and they have a lot of charge. So that's going to be number 1. And then between sodium chloride and cesium iodide, they're both +1, -1, but this one's a lot bigger, which again, the bigger they are, essentially there's a term that we use sometimes called the charge density. A small atom with a +1 charge, the charge is more concentrated. A big atom with a +1 charge, the charge is more spread out. So the charge density in sodium chloride is greater than the charge density of cesium iodide. If you spread the charge out, that's going to weaken the attraction. So this is going to be number 3, and sodium chloride is going to be number 2. Okay? Now, that's getting really technical into this stuff, but basically we have an argument we can make to compare all these molecules to each other. You don't have to say everything I said, but you need to give support for every time you make a decision on one molecule being higher than another, you have to offer some support for that. Give me the difference that you're looking at that distinguishes from each other. All right? Now, we do have, I gotta go back to the PowerPoint. Almost forgot. Okay, so now I'm on the next slide. We do have cases, though, where our rules that we're trying to apply don't work as well. Okay, so if two molecules are of similar size and shape, if one's polar and one's nonpolar, then we're going to assume if they're about the same size, the polar molecule is going to have stronger interactions, stronger attractions between the molecules, which means it'll have a higher melting point and higher boiling point. That's normal. Okay, but if we start looking at two molecules where one of them is a lot bigger than the other one, then what happens is at that point, the bigger, and this ionic compounds that we just talked about are wholly separate. We don't include ionic compounds in this discussion at all. We're looking at covalent compounds. If we have one covalent molecule that's a lot bigger than another covalent molecule, as we increase the size of the electron cloud, the polarizability becomes more important. And eventually, we can get to where London forces or dispersion forces actually become the major factor even over dipole-dipole. Okay? Now, specifically, if we look at methanol, CH3OH, and if you look at octane, which one would you expect to have a higher boiling point? Okay? So stop the video if you need to, think about it, write down an answer, and then start it back. So, if I look at these initially, I would look at this one and say, okay, well, if I draw the structure out, that OH right there is going to give me hydrogen bonding, which is like number 2 on my ranking list. Octane is a hydrocarbon. Hydrocarbons are always nonpolar, so that's going to be London forces. So if I go by my normal pattern, I would expect this one to have a higher melting point and boiling point than this one does. But if you look them up, which is what it asks you to do, you'll actually find that the opposite is true. So, this has been a test question before. Could you explain, based on what I said up here, could you explain why that is? Okay, and if you do think about it, octane, we look at the molecular weight, it's a much bigger molecule. The molecular weight of this one is a lot higher than the molecular weight of that one. And if the molecule gets bigger, then all of a sudden the London forces can get a lot stronger. All right, so that brings us to probably our last slide in this section, which is where we look at the 4 intermolecular forces that I ranked number 1, 2, 3, and 4. We initially assumed that they were all separate. We said hydrogen bonding is stronger than dipole-dipole, and dipole-dipole is stronger than London forces, and that doesn't give us the whole truth or the whole story. This slide actually shows it a little bit better, where nonpolar compounds that have London forces, they tend to have, if I go from low boiling point to high boiling point, or low intermolecular force strength to high intermolecular force strength, nonpolar compounds tend to be near the bottom. But it's a range. Smaller nonpolar molecules are going to have really low boiling points, but as I raise the molecular weight, or get the atoms to be bigger with larger electron clouds, the boiling point does increase. And it actually can get to the point where big nonpolar molecules can be higher than small polar compounds. And even some of the hydrogen bonding ones, they can come down. So it's a range where most of the time we can put them in this order, but that only really works if they're all of similar size. When the sizes are very different, then we can get some crisscrossing between these, and it makes it a little bit harder. Okay, so basically, we're going to use our rules. If I give you a set of compounds like I did earlier, we're going to use our rules, 95% of the time, and rank all our compounds, and we will usually be right. But every once in a while, you're going to get surprised and find out that one molecule is a liquid and another molecule is a gas when you think it should have been the opposite. And that's where you have to go back and look and say, okay, well, do I have a small polar molecule and a big nonpolar molecule or something like that? And you have to kind of reassess your properties to understand that. Okay, so that's a good place to cut off.